Thank you all. Thank you, the school, for the invitation. So I'm Giovanni Dettori, a PhD student at Polytechnic of Turin, and as Mustafa said, I'm working on AI, on NLP. Just to give you an idea, my topic of thesis is about AI for cybersecurity. So apply NLP on this topic. The topic is not your main, it's not social science, but the concept of NLP are the same. So let's start this lesson. As you can see in the title, today we will talk about NLP, so natural language processing and transformer models. NLP, you already discussed a lot about it. So is the AI applied to natural language, so the language that we use all days. While transformer is an architecture very important for LLMs and NLP because it is a breaking point in the history of AI. There is a before transformer and after transformer. Here there is an agenda, so at the beginning we will start with a brief historical background. Then we have a review part of the main concept you already discussed about the pipeline NLP, text processing, and ideas of embedding. And then we have some notebooks about code to try these things. And then there is an example with BERT that is I think you already discussed about it. And it is a transformer model. And finally, we will see the transformer architecture and the main models about it. So let's start. This lesson starts with these 4 questions that are questions about AI and NLP, because we see models as black boxes, but actually we see that they can manage a lot of things, but not everything. So, for example, the first question is, why can AI pass the bar exam but cannot learn to drive in 20 hours of practice? Or a child who touches a hot stove once never forgets why it hurts. Why does a model that has read about pain never flinch from anything? So why can AI describe in detail how to ride a bicycle but cannot learn to balance on a one? And finally, a child can learn what a dog is in 10 examples, while AI needs millions of photos and sometimes fails to recognize a dog. So these questions are just to start the lesson, and at the end of the lesson you know why this question. So to give an idea of the why, we can start with the stochastic part. This concept is about how LLMs works. Indeed, we cannot say that models think, but they learn patterns from data. So they learn very well to predict the words of the text we are creating. So this stochastic parrot says a parrot can reproduce the human speech perfectly, or quite perfectly. The sound, the rhythm, the right words in the right order, but it has no idea what any of it means. So it just repeats. So you must think to LLMs just as a parrot. They learn a lot. They know, and they know how to write things, but actually they don't think. And so the last sentence is NLP models read every book, and it is very convincing because we think that they are like humans. They're very good in this. So this stochastic parrot is a paper published, so you can read it if you are not convinced. To go even before this in 1950 we have a very famous person, that is the Alan Turing. During that period, the people was trying to understand if the machine can think and are conscious. So there were a lot of discussion about this topic, and there was not a solution because it's difficult to define if a machine can think or can be even conscious. So he changed the target and just say, a machine, can we tell the difference among a machine and a human? And so he defined this test that is a challenge among a human and a machine. So there is, in this case, we have a human that is a judge that cannot see the other two participants that are the machine and the human, the other human, and the judge can ask whatever he wants to the two parts and must, at the end of the test, distinguish among the two. If it is able to distinguish, the test is not passed, while if he distinguishes them, the test is passed. So nowadays the models are able to win these tests, so we are going further. But for a lot of time, the Turing test was the goal of machines. Here I reported just a pipeline, temporal pipeline, just to show you that the AI started a quite long time ago. In 1950, and to arrive to now with the new chat-based LLMs. So at the beginning, the approach was about rule-based, just to try to define all the rules of the language. So with just rules. It was quite rigid, so it was difficult to transform a language in rules, and so. Then we try to statistical NLP, then starting ML, machine learning, and all these things was about researchers. So only in academic university they was trying to use these approaches. Then very important, the word UVEC that introduced the concept of embeddings. And finally, the transformer I was talking about before in 2017, a breaking point in the history. And you can see the years are more close. So we have BERT, GPT-5, and finally ChatGPT. You already know, I think. And then the history continues with the new approaches and so on. Just to finish this introduction, I cited Yann LeCun. I don't know if you know, is one of the most important of nowadays people that are working on NLP, and it is always on the same concept that system can manipulate language and they fool us into thinking they are smart because they manipulate language, but in fact they are completely helpless when it comes to the physical world. So his idea is that LLM is not enough, so the models cannot learn just from text, but they need to learn about the whole world, and so have experience of the whole world. Okay, so if there are no questions about this introduction, if there are questions, please raise your hand, and we can start the fast recap of machine process language. Okay, so this is a glossary just to give a slide if you can return if you need. These are words that I'll use today. I don't know if you know everything, but yeah, maybe the most important one are token. We will talk about them in a while. The pipeline, also vocabulary and so on. Yeah, maybe something that we will not see in details after are the models and training. It is very useful to know the difference about training, pre-training, fine-tuning, and inference. So the training is the part where where the model starts from scratch and try to learn the patterns of the data to make prediction. So it is the part where we need a huge data set to give to the model and in a very long time try to learn something. Then pre-training is very close to training, but it means something that you try to learn general rules and not specific patterns. So just normally the models are pre-training and then you can fine-tune them on a specific task. So the fine-tuning is I take a general purpose model and I apply it to social science, so it is specific in recognize the I don't know the CV of a person. And finally, inference is when you use the model, so the model is already defined, and you give an input, a prompt, and you receive an answer. Okay. This is a 9 level of pipeline in NLP. So the main concept you need to know is that the computers, the machine cannot cannot use text. So they know only numbers. So they know only how to use numbers. So during the pipeline, we need to transform the text we write on the computer to textual output, to a numbers, and then these numbers are processed by the model, and then must be retransformed in textual output. In this way, we can read the output. So all these steps we will go later are these ones. So at the beginning we split the text in tokens, so in chunks. Then these chunks are transformed in vectors, so that are list of numbers. These vectors can be experienced by the model, processed, and then we have the answer. The answer is again numbers, so vectors that are then translated in the text, and we can read. So these chunks are aggregated together, and we have the output. So hello, I'm Giovanni, and the answer is hello. How can I help you? Okay, so the first part of a model perform is the pre-processing. The pre-processing is a phase in which the model, we try to transform the input, the human text into the input to the model. So the objective is to remove the noise inside the statistical patterns we have in input. So here I go through the main approaches. Not all the models use all the approaches. So the first is just we can see this example. So the first is lower casing. So we have the sentence, the chef Bob is baking delicious pizzas. Yeah, I'm Italian, so I put some examples about pizza. So just remove the capital letters, then punctuation removal, so we remove the punctuation, the stop word filtering, stemming and lemmatization, that is try to normalize the words, so baking becomes bake, and the sentence tagging. Sentence tagging is a process very useful for the models because we are transferring some knowledge about the sentence structure to the model. For example, here I put two examples. It is start and end, so we can say to the model that the sentence started with chef and ended with pizza. So if we have more sentences, we can use the tokens to split the sentences more. And yeah, as I said before, the goal is to reduce noise. However, we can remove too much knowledge in the process. We will see in the notebook these things, because if we remove too much words and so on, maybe the meaning of the sentence vary. For example, in some process we can remove not or is, so the meaning becomes the opposite. Then the second process is to remove. There is an error. Okay, is to split the text into base elements that are called tokens. So we have the first approach we, as human, we can think is about word tokenizer. We just split the text by blank spaces. So before the sentence Chef Bob bake delicious pizza becomes just split in tokens by the space, blank space. However, you must know that the models has a maximum amount of tokens you can store. So you need to manage this problem. So if you need to introduce a new word or maybe a new name or something else, but you have filled the model vocabulary. The model vocabulary is defined a priori during the training of the model. If you need to add a new word in this approach, you cannot manage it because it has finished. So normally is substituted by a unknown token. So nowadays we are using subword tokenizer. That is just if the word is inside the vocabulary, it is maintained as it is. So, for example, chef is maintained, while, for example, Bob, that is a word, may be split into two tokens that are B and OB. Indeed, in the vocabulary, there is always the alphabet letters, so you can always manage to split. However, the meaning of the token and the word is not preserved as it is. So, okay. As I already said, if you coin words or create new words, it is difficult to manage with the word tokenizer. So nowadays we use the software tokenizer. there are also other approaches, but the most important one is these subwords.
May I ask a question?
Yeah, sorry.
I apologize, I can save it for later.
Yeah, no problem.
I just want to clarify, thank you so much, by the way. For the sub-tokenizer, is this a problematic sub-tokenization, or is this acceptable? Because I find it, like, I was like, why is it B and OB and delicious altogether? Like, I didn't get the rationale.
Yeah, actually, this is an example I performed just for the slide. I don't know. Yeah, the model, maybe Bob is already in the vocabulary. Because actually what it matter is not the length of the word, but it is how much it is common. So if delicious is used a lot in the human language, so it is preserved. While if it is a rare word, normally it is split because there are not enough space in the vocabulary of the model. So this is why you have delicious maintained, but not Bob. Yeah, no problem. Yeah, if you want to stop me, no problem. Okay, now we are approaching the translation from the words to the numbers. So on the right part, you can see the vocabulary. It is what I was talking about. So vocabulary is, you have the list of all the words, the tokens that are in it. And so as you can see, the vocabularies nowadays are very big. You can see 100,000 tokens. And so this vocabulary allows us to translate the token to a number. That is something that the computer can manage. So you can see we have above the sentence we tokenized, and then we have the numbers that we can retrieve in the vocabulary. And for example, we have 2B, so the B of Bob have the same number of the B of bake. So this is a problem we will manage later, because in this case we are losing some information. And yeah, so in this way we have solved the problem of organizing number, the chaotic human language, but we have no context. We have just a list of numbers. We have not the meaning of the token. Just you can substitute a one with another number and no meaning. You cannot compare the number 38991 with 478. So you cannot compare pizza with delicious. So the model now has no knowledge about the tokens and the words they actually are. So now we try to transfer this knowledge with the example of pizza. And so we try to translate these numbers, these indexes, into mathematical space. So we can try, we have two pizzas, pizza margherita and Hawaiian. Margherita is with tomatoes and cheese, while Hawaiian has ananas on top of it. So in this example, I assign in my vocabulary the number 4801 and the number 4802 to the two pizzas. So this is my vocabulary, but I cannot make a comparison among the two pizzas. They are just numbers. So I try to define some features about them that is tomato, the amount of tomato, the amount of cheese, the amount of sweetness, and the controversiality. So, and then I assign to each one a score that, for example, margarita has a lot of tomato, a lot of cheese, it is not sweet, and it is well accepted by the Italian people. While the Hawaiian is less tomato, less cheese, it is very sweet, and it is very controversial for Italian people. So this, for us, becomes our vector of numbers that describe my token. And so you can, in this way, you can compare effectively the two tokens, so the pizza margherita token and the pizza Hawaiian token. And you can see in the graph, we can create, with a graph, the comparison among the two. This is just an example, actually, to teach you how the process is performed. However, the models, we don't know which number is related to something else, and which column, which number of the vector of this is related to a meaning. But in this way, you can, but it try to insert in these vectors the meaning of one of the tokens and so on. So I was talking, we can compare this with the these vectors. Oh no, sorry. These vectors are this one. Okay. Okay, then we can, so to have a graphical representation of the geometry, what we are making is that we can transform, we can visualize these vectors in the space. You already seen these ideas more times, I think. But so we can, if we plot these vectors in the space, here we have a 2D space. Actually, the models nowadays use more than 700 dimensions, but this is enough for us. And so plotting them, we can see also where they are located. So we can define a similarity among the points. So, for example, we can see that if we consider the topic of male, female, we can see that the vectors of male related words will be closer each other, while the female ones are close in each other. But if we can consider another dimension of geometry, and actually what we want to see in a model is that also if we consider the royalty feature, the king and queen are put closer respect to the uncle, the other ones that are common people. So in this way, during the training of the model, so when you have a huge amount of data and the models try to learn patterns, the main goal of the model is to try to learn these vectors. These vectors are called embeddings, and to put them in a way that all the semantic relationship among the words are preserved. So, for example, in the example I'm performing now, you have that in this space the male-female relation is respected, but this is not so good because king and queen are quite far from each other. So all the training has the goal of putting these balance around this space. Not as I said before, not a 2D space, but a huge amount of dimensions, 700 dimensions, and so just moving these ballots and understand what happened. And always, as said before, all these things are learned from the text, and so the last sentence. So it was observed a lot of text and tried to put the text, the words in the right place. So here we can find another important point, that is the type of data we use to train the model, because here we are putting the ballots in a order, in a manner that is retrieved directly from the data you give an input during training. So we have. There's a question? No. Okay. So we have another problem, that is that the embedding we are learning are not neutral, but are strictly related to the data set we use. So if we use a data set that is only where is present only the idea of, for example, Italian people, the model will output only the idea of Italian people. So we cannot learn something how the Turkish people, what they think and how they experience their daily life. So very fundamental is the data set we use. Indeed, in the models we are using nowadays are mainly related to the Occidental American data, because the majority of data they use to train their model has been scraped by data in internet, and a lot of the data in internet is in English, so the models can learn this. So a common example is that man is closer to doctor, while woman is closer to nurse. So nowadays this problem has been faced. However, if you try to chat with ChatGPT or other models, you can see that some biases about different things are possible. And so this problem has been shown by Bolubasi in 2016, and its focus was about related to male names with career terms and female names with family terms. So this was shown by him, and okay. So as I said before already, the main goal is that the geometry of the embeddings and what the model learns is directly related to the training corpus.
May I ask something?
Okay, so
When you say the model is kind of a mirror of its training corpus, so I kind of observed that different kind of AIs, let's say, grow claiming that it's going to be an anti-book. But how can it be possible if they are learned upon the same data? How different AIs have different like political leanings at the same time?
Yeah, actually, yeah, the main the main idea is that also depends on the time in which they have been trained. So the models that belongs to different companies and so on, they use different data in input, so they learn this. Also, another point is that the training methods are different by different models, so there are different approaches in how they are trained. Also, how they use the concept of the network that is present inside the model. So the organization also of the models is different. So you need to explore better also the architecture and how they have been trained. So the concept I'm explaining are very general. So if you want to go in details for specific models, the things are more complex, but can be managed, and it's also interesting to explore these things. Okay. And then this is very, in a very fast way, what is after the embedding creation. So there are some layers that try to that are the ones that are trained during the training, and so these vectors that are the embeddings are modified by these layers, and so we have these vectors modified. Then at the end we have different possible solution to our answer, and so there is a probability distribution over all these vectors, and then is depending on some transformation and other layers, they are one token is selected. So we have an Instagram, for example, and then we select the one with the higher probability to be selected. And finally, so we have the embedding, and then we have the tokenization, so we know what that embedding is, and so we can take the respective token. So I hope I convince you that the model never touched text, so we have the whole process to have to start from text and arrive to text. Okay, so this is the for very fast introductive parts. There are some questions about these topics or not? Okay. If there are no questions, I present the first notebook that is a fast notebook to see this concept applied in Python on the code. I shared with Mustafa the notebook. So we use different Python libraries, and so we will see these elements, so the pre-processing, the tokenization. One-hot encoding is the process of transforming the numbers of the vocabulary into some embeddings. So this, and finally we will see some word embedding. So also the bias part I was talking about before. So, okay, if we can go inside this notebook if there are no questions. Okay. Okay, you should have the, not this one, okay. Okay, you should have received this notebook. Okay, the link is directly to this project, so you should make a copy. Otherwise, it's a mess because everyone can change this project. And to make the copy, you should press on File and then save a copy in the drive. So now you can open the new tab and you can manage this. Okay, maybe I leave some minutes to make this. If you have some problems in opening a copy, please ask. Maybe we can make the break after this moment, before starting the notebook or not. I don't know.
Okay.
As you-
According to plan, the first session is 90 minutes.
90 minutes, huh?
more. Yeah.
Oh, I can go. Okay. No, I was thinking about 50.
12:30, the end.
Okay.
10:30, 11:30, 12:30.
Okay.
If you want to stop now for 10
No,
minutes, it's
for
okay.
me it's okay. It was just to not stop immediately because I was thinking about the 50 minutes, not.
Okay. Feel
Sorry
free
for
about breaks.
No problem for me. It was just for the others. Sono andato troppo veloce, eh?
Continua ad arrivare gente a caso.
Sì, a caso. Non sapranno cosa fare, però.
Infatti stavo dicendo, ascolta, quanto loro sono presi dalla navetta.
Comunque mi stanno registrando, quindi qualsiasi cosa dici sapranno.
Bellissimo, comunque fa freddissimo, cioè, in Turchia con la aria condizionata.
Ci sta. Va bene. Is there anyone with problems in opening this? Okay, so maybe I wait some minutes just for the ones we are not in the room. I don't know. Okay, maybe we can start now. Okay, so this is Collab. So you already used this during the winter school. So just a remind, we have different boxes, some text boxes and code boxing. So the ones you are looking now are text boxing, while below we have some text boxes that we can run by clicking on the play button. So during this first notebook, I selected a passage of the Little Prince book. That book I like. So I don't know if you know about it. So this is we will use sentences about this part. So I read it just to you know. So goodbye, said the fox, and now here is my secret, a very simple secret. It is only with the heart that one can see rightly. What is essential is invisible to the eye. What is essential is invisible to the eye, the little prince repeated so that he would be sure to remember. It is the time you have wasted for your rose that makes your rose so important. It is time I have wasted for my rose, said the little prince, so that he would be sure to remember. Men have forgotten this truth, said the fox, but you must not forget it. You become responsible forever for what you have tamed. You are responsible for your rose. I am responsible for my rose, the little prince repeated, so that he would be sure to remember. Okay, so we have the first box, code box, that is setup 1. Just to not go in details in the code complexity, I put here all the stuffs related to Python and import of the of the libraries. So as first we have some import of libraries that are functions that we will use. Then there are some definition of variables, so that are useful for example, the import of Hugging Face. Hugging Face is a repo where we can take a lot of pre-trained model. So as I said before, to train a model, it's quite expensive in terms of time, and also we need data to train. So nowadays we use pre-trained models, so models that have been trained by others and uploaded, for example, in Hugging Face, and then we can download them from Hugging Face and use directly in a few minutes. There are also other import very useful, so you can just execute while I'm talking. So I'm taking some time just to be sure it will work. An error message. Okay, yeah, it's also for me. So let's look this. Okay, yeah, because the models are not installed. So, well, this is just already the first. let's try if it works. So we need to, because the error was that a library is not installed, because in Colab we have only some common libraries. So for example, the Gensim one is not well known. So now we can try to run again, and then if it works. Okay, so you need to write this instruction. So this is an instruction to install Python libraries in an environment. So we need to write this. Okay, you must, sorry for it, you must add a code box. So if you pass, okay, I make it again. So if you have this situation, if you pass on the border of the code box, you can add a code box. Then put this pip install and the name of the library, that is Gensim. And then we can execute it. And I have that the library is already installed, so, but.
Shall we press import OS after we run the pip install test?
Sorry?
Should we press import OS after we install the Gensim?
You just press then play here. Yeah, you play before the pip install, and then you press play in the box. Oh, perfect. I like it. Okay, is it okay for everyone, or okay? Well, then here I reported the text I read before, so the Little Prince one, that is stored in the variable fixed corpus. So when we will use it, we will call fixed corpus. Actually, this is a list, it is a list. So as you can see, there are the commas. So we can also call one sentence by one sentence on the list. Then here there are some functions that we will call. So for example, normalize white spaces. So this function just if there are some double white spaces, it just keep one, or something other things. And so here you can see the for loop. This loop just print the fixed corpus, so the sentences of the passage. So we have print them with the number, the index of the row. So you can see the number 1 because we have this print here. Okay, if everyone run this, we can start with the pre-processing. So the first process is to lower the text. So we run the function lower text, and then we can run the part below. So we can press play, and we can see that the starting sentence was what is essential, and then we can lower it, and we just remove the capital letter of the W. And yeah, this process is performed just by method of the of Python that is .lower, that just make the text lower. Then we can remove punctuation, and so here this function just take the string input and remove all these possible punctuation symbols. And so if we press always play, we can see the transformation. So we have removed the comma and this sign. And okay, so okay.
Explain why does it show syntax warning, invalid escape sequence? What does this mean?
Sorry, the?
So yeah, it shows syntax warning.
Ah, yeah, okay.
So what does it mean actually?
Yeah, actually, because this is a regex, so because in Python the how to say the square paragraph is used also to for the list and something else. So here to make this working and recognize it, you should put another bar letter. In this way you can recognize it. But yeah, actually it works also in this way. So yeah, because now actually here it is inductive to visualize this as the two symbols, or just to consider it as one symbol. So because the backslash is used to say, oh, I'm using a string, a char, and not an escape char. I don't know if it's clear. It is. Okay. So here we have then the stop words. So we can remove some words, because to reduce the amount of tokens you need to process, you can remove some stop words. Stop words are like the the words not, the words is. So for example, if we run this, we can see that we have removed some parts that are useful for humans, but not quite useful for the machine. For example, if you read the first one and the second one, you can actually manage the meaning of the sentence. So what is essential is invisible to the eye, the little prince repeated, and the sentence below is essential, invisible eye, little prince repeated. So we have removed these stop words to reduce the number of tokens we need to process. And in this case, the meaning is preserved. So it's okay to remove stop words. Yeah.
Should we expect whether the meaning is changing if we use words like not, but, because these kind of words are changing the meaning? Should we expect?
Yeah. Actually, we should inspect it, and then there is an example where I show where this approach fails. So actually, all these things, if you use ChatGPT or something like that, are already performed by the model, and how the pre-process of the text is performed by the GPT models. This is just to give you the idea that also if you need to make some pre-processing in very specific cases, it's important to look at if the meaning changes or something like that.
I asked that because I'm thinking to perform all these tasks for a book, like 400 pages, but I think it's not that preferable to do that because after doing all this stuff, presenting for some sentences, the meaning can change.
Yeah, the meaning can change. Yeah. Indeed, in a while I show you just a sentence where if we remove not, the meaning can be the opposite of what actually the sentence means. So yeah, it's a problem. Yeah, because we need always to find a trade-off among pre-processing. Because if we decrease the number of tokens for the model, is better because it learns less noise inside the data. So and we have less tokens to process, so it is faster. But we need to pay attention to not lose some information and so on.
Haven't we lost a little meaning in this one? Have we not lost a little meaning in this one?
I don't know. You are more expert than me. Yeah.
I mean, in social science, that's very important because what we are all working with is meaning.
Yeah.
Cultural meaning.
Yeah, indeed. I select this example just because it's important for your topics and so on. Yeah, because in this case, I mean, I think that in a machine point of view, the output will be quite the same as removed. It is not how to say. We have removed information because we have removed information, but the meaning is preserved, at least for the machine.
Two questions. First,
Yeah.
you get a change in the meaning, like, when you move not. So what do you do then?
Yeah, actually, this is an example what in pre-processing you can perform. Actually, the models nowadays does not make these things. They manage these problems in automatic. So if you just load from Hugging Face a pre-processing pipeline, so you put pre-process, it performs the operation in a way it is able to not remove some the knowledge or the meaning of the input. So this is just to give you which are the possible steps that a model can perform.
So these steps are not all any longer used, is what you're saying, right?
Actually are used, but in a clever manner. So they select what to remove depending on the meaning. So when we will see the, for example, the BERT example on the models, we will use in the pipeline just pre-processing. That the pre-processing is automatic. So in this way, maybe the stop words is not removed, just some not useful one. But this is something that you'll never see if you work with models. Also in Python, you don't write this function, but you use the pre-processing stuff that works well. The people manage all these stuffs in the pre-processing. I don't know if I convince you. But
I'm not really very convinced because if this is no longer used or if this is, there are much more advanced or better ways to do it, then why not just start directly with those ones?
This is a good question. It's just because when you manage to perform to create a data set for a training, I don't know if you will create a data set for a training or for a fine tuning. When you pre-process the text, this is something you can face because yeah, during the example I'm performing is not strictly related to the pipeline of the model, but in the pre-processing of datasets. So when you collect data in the world, and then you need to pre-process to spread with others your dataset. Normally you didn't share the trash data. You try to clean them and to give to the data an organization and something clean. So when you pre-process them, you need to consider these things. So which are the possible things that you can perform, and the things you can do, actually you need to pay attention on them. So this is why I put this, but this, yeah, very dummy, this solution. I'm agree with you that nowadays it's not performed, so yeah.
Excuse me.
Yeah.
Is there a limit of text that you can put here to process?
Actually, here in this solution, you can put the length you want, because it's just a Python function and so on. Actually, in the models, we have the problem of the context input, so you have a maximum number of tokens that is very high. We can put thousands of tokens in input, but yeah, here you can.
For example, let's say you're doing a study and you have to analyze newspaper articles.
Okay, yeah.
Okay, you have data maybe from 2000 up to 2026 of Turkey, all the newspaper articles ever written. This is going to be a huge chunk of data, and you put it at once.
Actually, you cannot put on once, so you need to perform. There's some techniques to manage this that are related to how you organize your data. So normally the best approach is to try to summarize each one. So you give a paper to the model, summarize it. Then you try to summarize all the papers, and then you can try to aggregate the information you retrieve. But yeah, this is an open question. So nowadays the models are always bigger and bigger. They try to increase the number of tokens in input. But yeah, now we are arrived to 1 billion, but I think the biggest one. But actually, this is not a solution, because then the information by the model are actually lost during the solution. Okay, then always with the idea of what we can perform is the lemmarization. So we just use a lemmatizer, and okay, we can see that just we have removed the ED part. So actually now we are losing other information related to that is an objective and so on. So this is the question we already discussed before a bit. So the meaning of the sentence, we lost something, and so if we run this this cell, we can see the example now with in the last one we have the sentence, but you must not forget it, and we obtain must forget. So okay, the meaning is now the opposite. So this pre-processing pipeline is not good, and so we need to find some solution to, for example, not remove not. For example, if we just remove from stop words the word not, also the other the other sentence we have must not forget, and it is semantically related to the first one. Okay, now if you want to try to play a bit with just putting some sentences here, you can see what happened in the depending on the sentence you put. I give you 1-2 minutes just to, if you want to read what each function perform, or try to play with this sentence. And I'll drink a water.
Why did the roads change to rise?
Yeah, because you have the the problem of that lemmatized change also the time of the verb. So rise is the present of rose, and so it put rise.
The word. It's a noun. It's Giovanni. Oh my
Yeah,
God.
these are the things. Yeah, these are the things that if you don't pay attention can be interesting.
I think I'm not going to use this.
No. This is very dummy.
And now my fear, when I'm working with cloud, for instance, when I put my text on the cloud, is that cloud how it
No.
reads my text? Yani, if that's the case, I might not use it.
No, they manage well these things. But yeah, these are the problems that if you try to make the things directly in very low level, so starting from scratch, and you must manage also these things.
I mean, how reliable or even the BERT or something other models that you said are pre-processing the information themselves? Do they work like this?
No, they manage correctly the things. These are just dummy examples to give you the idea that this problem may exist, but only in the case you use the code from scratch. So if you want to implement a pipeline very low level, so starting from pre-processing, you must manage. But if you use the pipeline well established, or ChatGPT, they perform these things very, very well, so they manage these things. No problem for you.
So we learned in winter school that lemmatization, often when you lemmatize the text, the voice is always lost, the subject and object, who is the subject of the sentence and who is the object of the sentence. In that case, if I'm giving my text to BERT, for example, I need to keep the voice, whether it's an active voice or whether it's a passive voice, who's the subject and who's the object. Can I use a code or something to get around that thing so it understands to keep those things or preserve those things?
Yeah. Actually, you can. Yeah, because the lemmaization is. For example, you can not perform the lemmaization, and you can maintain the words correctly. Yeah, as they are. But yeah, actually, if you perform the lemmaization, this is a problem that you can face. So.
Apologies if you addressed this before. How, like, when we detect such an error, what can we do? Like, what's the road we should take?
Yeah, actually, you can remove the lemmaization, because the process of lemmaization make this. So in this case, you save some tokens because you don't have more for example, in the example before, we should have used 2 tokens for repeated and 1 for repeat. So if you use lemmaization, you have this, but you lose information in this case. So you can, for example, search online, and maybe there are some there are more clever lemmatizers to use in this case. Yeah.
I have a question. Under the exercise, is the lemmatized is the text? What is it about?
The lemmatizer is the process of trying to standardize the words. So if you have, for example, a word that finishes with ing, you remove ing because you are bringing the word, the verb, to the standard form. So if you look at, for example, at this example, no, we have this sentence that use rows. That is, in this sentence is related to the flower, rose, but then the lemmatizer thinks that it is a verb, so the sunrise, and so it put this word rose to the base form, that is rise. So the lemmatizer is trying to normalize the words to the base forms. So yeah, this in some cases can be a useful approach because you are reducing the noise and the number of tokens you need to process. Sometimes you lose, for example, in this case is terrible because you are losing very important information. Yeah, you are changing completely meaning. Okay.
Putting like functioning the stop words in the last step can be a solution.
Sorry?
Like functioning the stop words in the last phase can be a solution because stop words is kind of changing the the meaning. Because I just tried your example, but you must not forget it.
Okay.
The problem comes when you function stop words in the same example. Lemmatization is not a problem, but removing the stop words is the problem.
Yeah. In this case, yeah.
I didn't get that.
Yeah, the problem is, if I can summary. Yeah, actually, depending on the sentence that you use, one of the point of the process of the preprocessing can be the problem. For example, in this case, if we perform the lemmatization, it is not a problem. The problem here is that we are removing stop words that are useful. For example, not. So yeah, depending on the sentence we are preprocessing, it the problem can be the different part of the preprocess.
So as a researcher, I say I'm going to do research and I expect this kind of problem to happen. How do I minimize that?
Actually, for me, the main approach is to just take the preprocessing. For example, from Hugging Face, you can directly download. You can use the command function that just dot preprocess. So you give the sentence. So in this way, you can manage it. It is managed in a clever way, so you can manage. If you want to go in details, you need to, depending on the sentence you are processing, you must change the things and so on. Okay. I don't know if it is time to break now, okay? So we can make a break and then we restart from tokenization. Okay, well, we can start again. Okay, since you were very interested in how actual it works, the pre-processing, so I'm trying to make some freestyle about this. very quickly just to give you an idea. So now I'm installing the transformer library, that is the ones that arrives from Hugging Face, so the ones you can use to use the models in Hugging Face. And then so here we need to load the model. So we are importing the basic tokenizer. So this is the class in Hugging Face always. I write it not correctly. Transformers. Now, okay, so I'm importing this library, and then we just load a model. So, for example, we define the tokenizer. So, tokenizer is always the one for pre-processing. So here we have this. Then we load the model from pre-trained. This is just a method defined in the class autotokenizer, and then I need to so this is Hugging Face. So I can search for the model, this BERT base. Okay, for example, since I opened these, we can see that of the base model of BERT, we can have the base one, that is this one. Then we have some fine-tuned version about multilingual case and fine-tune. So, for example, I need this string here. So here I put the name of the model, that is this one. Okay, then so I need the text. I don't remember the sentence was this one. Okay, no, wrong. And then we can use this pre-trained model that is in tokenizer, just tokenizer. And then we pass the sentence here. Should this one. And then if I execute this, okay, here we have the tokenized version of this. And in this case, it didn't remove anything. I think, yeah. It just left everything as it is. Yeah, maybe the idea is that because the vocabulary is so big in BERT, so for these words can be stored easily. Then we could play a bit with the sentences to try if there are some cases. For example, if we put everything in capital letter, let's see if. Okay, no, actually in this case it is not performing pre-processing, so I selected the wrong example. So the choice of this pre-processed model is to pre-trained model is just to split in in tokens the input without pre-processing. So yeah, can happen. Are some solutions. So this is everything. Yeah, actually here there is a small spoiler. We will look later, because as you can see, since the BERT haven't applied some pre-process, it is the essential remains it remains in capital letters. So in this case, it is forced to split it in these parts. So we have more tokens for the same words, while if we can see, no, I write it as in a wrong way. If we put it in the lower case, we have just one token for this word. So as before, the pre-processing is important, but yeah, to not waste meaning in BERT, for example, we have that the pre-processing is not performed. So okay, we can.
Can I just interrupt for a second?
Yes, sir.
Is
Sure.
there any easy way to copy this to us and send in a way? I don't know about the organizers. John,
Okay.
falan kopyalayıp bir yerden çözüp,
Maybe actually, if I modify this, if I put here, you should see, because the yeah, if you go not in the copy but in the previous one, I put also the how to install. I don't know if you see now. Okay. Okay, well, maybe you need to run again the setup part, because if a lot of time passes, the model may, the collab may lost the things, so the libraries and so on. But okay, now it's okay. Okay. Well, this is the tokenization part. We already seen the final output. Now we go deeply in the different steps. So here we have again the fixed corpus. I put here just to have a copy. Then we have this instruction that it is to define the vocabulary of the. So we are downloading the vocabulary of the model from the Hugging Face. So here we see the bar. So we can see that there are 466,000 of tokens. And so here this command is just to output the frequency of the words in the corpus. So here that are in the vocabulary. So for example, if you count the number of D words inside this corpus, you can see that there are 10 occurrences of it. I reported this just to show you also that the fact that the vocabulary is built following this idea of frequency of words. So if I need to choose among two words to put in the vocabulary, the words more frequent in the training dataset is put instead of the one less common. So in this way, the two are selected. Okay. Then I run this part. So this is so I selected 3 sentences, and this is just to show you how they are split. So in the first case, we have here we have also the difference among the word split and the subword split. So as you remember, the word split is just blank white space based, while the subwords we can have also the single word split in 2 or 3 and so on. So in the first case, we have that the 2 are the same. So because all the words are inside the vocabulary. In the second one, we just have the dot removed because it is not present in the dummy vocabulary I created in the whole word. Okay, then we have another sentence that is you become responsible forever for what you have tamed. So here we have a problem here because the word tamed is not present in vocabulary. So since it is not present in the whole word, we just put a noun. And why in the subwords we have the split, tame, and the. To stress this problem and to convince you that the subword is better, I just put this sentence without white spaces, just because the student has wrote wrongly in it, and we can see that in the whole word this word does not exist. So we have just a noun. So we lost every information. While in the subword we can preserve some meaning. So because the words are we can have the tokens to split it, and so we can preserve the meaning in a way. Oh, sorry, no. Now, okay. Perfect. Okay. Here I left 1-2 minutes to try if you want to write some words, some sentences here, just to try the vocabulary of this model. And if you when you try, you have some questions about the words you put and something like that, you can ask. So I wait just 1-2 minutes if you want to try the. Yeah.
Can you repeat that process?
Yeah, actually the process is the one I wrote before to try to show you the preprocessing. So, for example, there are a lot of ways to perform it. This is the basic one. So this is a class, Python class, that is called AutoTokenizer, that is inside transformers, and transformer is the library of Hugging Face. So from this we can just say from pre-trained, and here we put the name of the pre-trained model. So as I showed before, here you can search for a model. For example, here you can, for example, I was searching for BERT, and here you can see the basic form that is, for example, BERT base. And then you can also have some other models. For example, this one is fine-tuned on understanding different languages. So normally the basic models are only in English. This is fine-tuned to try to learn to talk also other language. So here you can search for the best model. Normally you can search online which is the best model for this target, and then you can you need to copy this this name. So it is inside this BERT. Actually,
When you say best model, best in terms of what, how can I?
you can search for the community, the number of download for months. For example, here you can see that
Like,
the
what is a good number of downloads? Can I trust that? So I can trust to some extent.
actually, if there are a small number, you can I don't know the specific number, but a way to see, for example, is this one, because this is the community. So for example, this is the community of BERT. BERT is a very important variation of BERT. So if you take something from this, you are sure or quite sure that is good and has been controlled. So for example, here for example, we have the NVIDIA models. So this is for image processing, so it's not, but it is for in the NVIDIA community. So you are quite sure that are good. So if you instead take some, for example, I don't know, some not proprietary models or some, I don't know, these ones, but are not so known, you must check about it. But you can take the name and check online if this is a scam or something like that. Maybe, I don't know. So this is just to give an idea of Hugging Face. But there are a lot of information online about this, so you can search and manage this. Okay. Well, so now we have the tokens that we can use. Then we need to translate the tokens to numbers, so to associate to each token a number. This is the scope of this cell. So we have this sentence. Then get subword tokenizer is not defined well. Okay, this is the problem I said before, because it collab normally after a while that you don't use the cell, restore the environment, so you need to reinstall the things. So we need to reinstall gensim. Okay. Okay. So I think also you must perform the same. Okay. Here we have again downloaded the vocabulary, and then considering the vocabulary of this model, we are associating to each token an ID. If you load another model or another tokenizer, you can see different IDs. It depends on the choices of the people who train the model and define the vocabulary. So here just to know, and we can see that there are no relationship among the numbers of different tokens. So just like this. Now I'm actually in this level of translation of the number is just an ID associated to the token. Then with the code I run in a while, we can translate these IDs in embeddings, so in vectors that preserve the meaning of the words. So this is just to we associate a number to a token. Then here we see we are trying to give, not here but in part 4 where we have embedding, we try to give information here to display this embedding on the dimensions of the embedding. So this is just an idea, just
So it depends on the proximity of the numbers to
no, actually, you at priori, the people define a vocabulary and say the token U is number 1, the token R is number 2, and so on. So you just like a dictionary in language. So you have the name, and then you associate an ID to it, and this ID is right only on this vocabulary. So if you take another model, the number 2017 maybe is another word. Okay, it's just a number. Okay, so here we have an example of one-hot encoder. That is a solution. The first solution that we can use to pass from these numbers to something that the machine can use. So, for example, we have the idea is to arrive to a vector. So, starting from the number to arrive to a vector that then we can change and use to display in the space. So, taking this sentence, you are responsible for rows. We can pass to a vector, something like that, just putting all the zeros except for one to the words we want to consider. For example, I chosen the token responsible, and then running the cell, we can see that in one-hot encoder, the responsible is in index 2, 0, 1, 2, and so we put 1 in the third position. And this is in this way we can consider different words. For example, if I put here the U and I run again, we can see that the 1 is in first position and so on. So in this way we can define a vector that are different to represent each token in input. So this is a possible solution. The problems of this solution is that you need to put a lot of zeros, and the only bit of information is this one, the 1. So if we consider that a normal used vocabulary is of this size, we should have a vector of 466,999 zeros and just 1. So this is not so efficient. So this is just a way to have a vector that represents each token. Okay, so here is because we need the embeddings. So these embeddings is the name of these vectors that try to store the semantic meaning of a word inside the vector. And so here is the same, is the same image I showed before. So the goal is that vectors that are of this same topic or are related are close, while words that are of different topic are far. Okay, so now to this is another setup part where we are using this model that is Glove Wiki GigaWord. That is always pre-trained model. We are loading it from the Hugging Face. So thanks to get embeddings. So this is a function that we defined in the setup before. So now we have downloaded it. So we have this pre-trained model, and then we can use it to see if the embeddings we have obtained are related or not. Okay, so the vocabulary size now is slightly smaller, and the vectors we are using are about 50 dimensions. So now, just to give an idea, we can run this part. So I selected these three words, and in the here we have the word, and here is the list of the closest words to this other word. So we have earth, and the ones that are the closest one are listen. So pain is very related to earth because this is a score. It is the confidence score, so how much the model is sure about these things. So about this prediction. So we have these words. The same for essential. So it is related to vital, ensuring, necessary, basic, ensure, dependence. So we can see all the words. If there are some errors, you can see them because there are. So in looking at these words, I think that the people who made this glove perform a quite good job because all the words that are close to the earth, for example, are semantically related to earth, and so on. And so now we can return to the problem of rows, and sorry.
So basically, for example, let's say, like you do interviews to collect qualitative data, and then we wonder, let's say we have interviewed 20 people, and we wonder, okay, I have like 3-4 important themes, or let's say words which are important for me, and I want to see among my participants which one is related with which one based on the data. So I will upload, let's say, this 20 interview, and then when we make this code works for, let's say, 4 words, and then it will give us how closer they relate with the other words.
Yeah.
How it decides which words will be there, or like will give us like the nearest 5, or we will limit it.
Okay. To solve this task, that is a higher level task. Actually, you need the model. So we will see an example like that in the afternoon, I think. That extract form you can give also to the model, for example, to BERT, the entire questionnaire interview, yeah, and it gives you an aggregate point that is the score, and you can use this score to compare them. In this case, and yeah, it works similar to this, but try to aggregate also different bankings. Because in this case, we are working directly on the the token. So you can just compare not aggregation of information, but just how the model has put together the embedding of a token.
Because here the data only is tokenized.
Yeah.
Okay.
Yeah, they are just I just take Earth, so a token, and this token is inside the vocabulary of the model, and then I compare this with other words that are inside the vocabulary, and I'm computing the distance among the two, and so this is just a qualitative result, so you can just play with some words and see if the embedding space is organized well in the model or not. So, but for the work you are mentioning, there are some solutions that we will see, and yeah, it is with BERT you can manage this. Okay, so we can return to the idea of yeah, sorry.
So let's say if I have a word healthy.
If you have?
Text, healthy.
Ali,
Will
okay.
it be, associated with heart, or will it be associated with responsibility? Because it's a very gray area. If you are healthy, you have a very good lifestyle and you are responsible, but at the same time, health can be related with heart. So how does the model try to...
Yeah, you get an important point that yeah, the only way you can play with embeddings is the training corpus, so the data you use during training. So these are patterns in the that the model learns in the data, and actually also the things that I showed to you is quite a simplification of these are qualitative ideas to try to understand what it is inside a model, but actually yeah, the things works. This is what we know, and yeah, we have that related words should be close to each other, but we are not sure it happens. There is a technique that try to solve this problem during training that is called the contrastive learning. That try to you have there is a fine-tuning solution. So you have a data set with the answer, and then you try to put the embeddings to change the weights of the model, to put the embeddings on the fine-tuning data set far away or not. The idea is to in the data set you have for example a sentence that is in contrast with the second one, and you force the model during the training to put the embedding of the two sentences far away. So you take the BERT, for example, pre-process, and then you perform this fine-tuning that is called contrastive learning. Let's try this. But this solution is focused on yeah, if you want to let the model solve one specific task, so you force the model to learn something you want. So this is a possible solution that you can use, but yeah, actually we have no direct control on the embedding, so yeah, only in training and so on. So now we move on to serve what works with rows, the problem we already output. And so here, if we run this, we can notice that for this embedding, rows means something that rises. And so the most related words are not the flowers or something like that, but are related to fell, climbed, jumped, and so on. So in this case, rose is not related to the flower.
Is this the list of the words close to the word rose, kind of vectorally?
Sorry?
The words you listed, these are the words close to the word rose vectorally? These are
That's the question.
yeah. I'm trying to understand why you got this list of words. Is it because you are trying to get the words kind of like a word cloud, the words, the list of words appearing around
Yeah.
the word?
Yeah. The idea is like that. Yeah, you can imagine this as a point in the space, and then we have rows, and the closest point to rows are this one. Okay, thank you for the question because it was good.
So when we notice that this does not align with what the meaning is, do we have to choose a new model, or?
Yeah, it can be a solution to try a different model. Yeah.
These are the words that usually come with the rose word, or are these the words that have the same meaning as rose?
They are more semantically related. So for the model, fell is very related to rose as a word. So semantically, so you can choose two words and they are semantically related. So for example, I don't know, men and women are semantically opposite because female and male, but are related because they define the gender of a person. So in this stuff, semantically in this way. So rose and fell are really close in the space because means something very close.
But they usually come together, but they don't have the same meaning. For example.
No, actually, they have a very similar meaning. So for the model in this case, it could use the word rose instead of fell. So in a sentence, if you want to write a sentence, maybe you can choose rose or fell in the same way. You can think about this way. Yeah, but always, as I said before, it is a qualitative way to explain the things. Actually, we don't know very well how the model manage all these things, but we have we have these vectors that are learned during the training, and you use it and it works. Okay. Now we try to visualize the embedding. So here, yes, we can see the code. Just to know here, we have that, as I said before, the embedding have in this case 50 dimensions, our vector of 50 dimensions, and here we are trying to reduce the dimension in just 2 dimensions. So we are taking the 50 vectors and transform it in just 2 dimensions, and this way we have this situation. We can see the rose one here, and then we have the words related to botanical in orange, and while in green the part related to the relational part, because in the Little Prince actually the rose is the flower because the Little Prince has this rose, but actually is talking about sentiment and also the relation among people, and so in that sentence, rose also have another meaning that is relational, and so here it's a try to show how the embedding are positioned. So you can also try to change. It's quite interesting to change even if just one word here. So for example, if I delete garden, so the
the display changes always, because the problem I said before, we are transforming vectors of 50 dimensions in 2 dimensions. So this process is called PCA, and so every time the display changes, but we can continue to see a little bit the 2 clusters in the data. So maybe it can be interesting to change this. For example, if I had a word, for example, related to fall, I put here, it is wrong, but because it's not a relation word, but just to see, we can see that fall is the closest word to rose, and yeah, just to see.
The distribution here is based on the model that we already uploaded.
Yeah, we are using the embedding computed by this glove. Sorry, this model here. So always, if we change the model we are using, the situation changes. Okay. So here we can see the main problem that we need also to further solve. That is the fact that we have just, for rows, we have just one vector, one embedding, and we cannot change it depending on on how it is used. And to solve this problem, the transformer is the architecture that we will use. Just to complete the scenario, I prepare also just to show you some social biases that I was talking about before. So here, if you run this cell, you can see this graph. So we have in orange the words that are more related to the word E, so man, and in green the she one, so the woman. So we can see that this model is thinking that, for example, a boss occupation is just for men and not for women. So here it's interesting to see which are the biases the model is performing. Also, in this case, if you use other models, maybe the solution are different. So you can see other patterns and other interesting things. So the same for some adjectives. So also here, some related to he and man and woman. So also here it's interesting to see, for example, that for this model the men are strong and decisive, and while the women are caring, so related to, for example, the home and the care of kids and so on. And always this is because during the training phase the model has learned these things. So the data, for example, he read more sentences about male bosses and women that are at home and carrying the kids. So this is just to conclude 3 takeaways. So the preprocessing, as we learned, removes noise but also meaning. Then the tokenization is important to preserve the words, but the vocabulary has a fixed size. And finally, the embedding are good because they learn how the word is, what the word is, but we can not put together some relationship to other words that are in the sentence or something like that. Then here I prepared a very fast quiz just to focus on the main things we discussed. So I give you some minutes just to make it for you. Your answer will never be judged or something like that. It's just to see for you if you have understood these things. So you can make them. You have on the notebook, and so just a few minutes. Yeah.
Given the kind of biases that we have observed, a skeptic may say that when you use it to study social events, you may not be able to tell the true picture.
Okay. Yeah.
Particularly, let's say you do a study on Turkey, and then you find that, for instance, this kind of bias about men and women, when in actual fact what we have observed in recent years is not always the case in most cases. So how do you know any software that one can use to avoid these kind of bias, or is it a possibility that I can retrain the model myself?
Yeah, actually, yeah, the training in general is a very demanding approach, because you need data, clean data, and also the time, the GPUs to run the models and so on. Nowadays the common used models, so if you use ChatGPT, Gemini, or Claude, or DeepSeek, and so on, this problem has been recognized in the 2016. So they are trying to normalize the data to reduce the number of these patterns. So if you use the new models, still if you play with ChatLM, you can see them. There are some blogs where you can see some prompts to put that, so you can experience. But there are some solutions that try to make it. So I'm not expert in this, but I know that there is also a fine-tuning approach that can help in this. But you can search and find something else. Yeah.
In the field of psycholinguistics, there is a term, there is the literature called incremental sentence processing.
Okay.
In this, the idea is that the system takes each word one by one and predicts the next word.
Okay.
Is there any model similar to this, and if so, how sensitive?
Yeah, actually, the way the models are trained is, for example, after we will see the structural transformer, and there is the encoder-decoder structure. The structure of decoder is something that it predicts the next token. So it's how the model works. For example, ChatGPT or Gemini and so on, the whole models. If you see when you write a prompt, it writes the tokens, and it does not print immediately the solution, but writes token by token, because in that moment it is writing token by token, because it works like a loop in which, given the input, it tries to predict the next token and go on. So this is the approach. I don't know if this is the question you were making, but this is the approach in this the encoders works. But I don't know if you have some specific I don't know topic.
I was just wondering, this is an assumption, or this is humans actually contract sentences incrementally word by word, but they predict the next sentence.
Yeah.
But it fulfills the previous sentences requirements, and it interprets as a sentence.
Actually, this the decoder solution. Now I didn't explain it, so it's difficult to say. But in the decoder solution, you have and it is how the current models works. You give the prompt, that is the sentence you give in the chat. Then given to that prompt, it tries to predict the next token. So it takes the answer is just the prompt plus the tokens predicted. And then on one time, the model set a token, say stop, and it stops the production, and you have the answer. So this is how it works. It's a spoiler for the future, but
Giovanni, should we go for break 10 minutes?
Yeah, okay, it's okay. Yeah, it's good for me. This is the last part of this notebook, so it's perfect to make a break. So
Do we get the answers?
yeah, if you want, I can give you the answers. Actually, I didn't write them, so freestyling also in this case. So okay, the first one, important risk text pre-processing. So this is why we have remove meaning. So if we the pre-processing remove meanings. So the others one are not related. So why can stop word removal sometimes be a problem? It may remove words like not that change meaning. Why is pre-processing described as interpretative rather than neutral? For poets, because each step reflects a decision about. Yeah, the third, because each step reflects a decision about what matters in the text. So, yeah, if you pre-processing, you remove something, you have this problem. Why do NLP system tokenize text? This is because we need numbers. So we need units. I think this is the first to make a reward positive, remove or reward. Yeah, see the first one. What is a likely problem with a fixed whole word vocabulary, and it cannot include every new or user word? Then why are subwords tokenized useful? They can split unfamiliar words into smaller long pieces. In an embedding space, words that appear in similar contexts are usually located near each other. So the third, why can word embedding reflect social biases? Because the third. So because the geometry is learned from human written corpora, so the data set and input. And finally, we see the practice when using embedding. The third one, because you need to check the training data, and you can see if the embedding are outputting what you think. So I think these are the answers. So you can make a break and then continue with the last thing of the morning. Thank you. Inside the model. So here we have the two sentences. Now the little prince loved his rose, and the sentence B, the sun rose over the desert. Up now, with the things we have studied up now, we cannot distinguish rose in sentence B with rose in sentence A. So for, as this sentence said, for for basic classification or some basic modeling, this solution of just embedding can be useful. So all the models that are before the transformer paper, so before the 2017, are based on word-to-vec. That is this approach of just learn some embedding related to arrows, to the token it is. So the things that we need to add is something that is related to the how the sentence is structured. So you can understand as human that rose in sentence B is related to the sun, or to the rose, the flower in sentence A is due to the context of this sentence. And so we can see that rose in sentence B, for example, is related to sun. So we can link very deeply these two words together and understand immediately what rose means. Instead, in sentence A, actually, the writer of Little Prince used this rose in a more general way that you can understand as a human. Also, as a human, it's difficult to understand the meaning of rose in that context, because if you read the sentence alone, you can immediately think to the flower. But actually, if you read the entire book, you can see that rose actually is the it's a relation among people. So how it's the relationship among people. So you need to take care about friends, about the relation of people on which you live in in your life. So very important in the language, human language, is the how the words is actually used. So the same is, for example, if you make some jokes or word jokes and so on. So it's very important this. So the token alone, a meaning, can give you some information, but it's not enough. I hope I convince you that it's not enough. And now, we need the context. We need how the model, how the words inside the sentence. So now we will see directly the solution of BERT. So BERT is a transformer-based model to see what's changed, and then later we will see the more architectural part. So we can try to understand what the transformer is and how it works. Just to give you a context before the notebook, the BERT is actually are the initial letters of bidirectional encoder representation for transformers. Now these words are not so meaningful for the majority of of you, but the idea is that it is able to learn things by reading the entire sentence. So it is bidirectional. It can read in both directions. So this helps him to link the words to the correct part of the sentence. Then it has been pre-trained on massive text. So they took all the Wikipedia information, then plus the book corpus, so terabytes and terabytes of data. And how they train it with these two techniques, that is the masked language model and next sentence prediction. In a few words, the masked language model is just, I give you the sentence, then I hide to you one word or more words, and the model must predict the right words in the masked one. And while next sentence prediction is something like it was talked about, so I must predict the right words after the one. So I give you Elohim, and the model must understand that a name must be put after Ein. And then also here we have the fine-tuning, that are the tasks that allow the models to learn some specific patterns and some specific tasks. For example, with BERT, we can make classification, question answering, sentiment analysis, and so on, and near. And so with one architecture, we can perform different things. And so, yeah, there is also the importance of fine-tuning, because we have BERT that is pre-trained, the one we loaded, but we need to actually fine-tune models to make specific tasks, because the pre-trained one is only able to perform the masked language, the masked challenge and the next sentence prediction. So it's this one. So we will try to go from the embeddings to have a context-aware representation, something that consider the context in which the token is present. Then here there is the notebook we will face. I think that after the launch we'll see the notebook. So the idea is to give you, show you how, for example, we can use BERT and what is able to do, and to convince you that it works, and then we can see how it works and what we can do with it. And so, these are the libraries we will see, transforms, and transform is always the one of Hugging Face, while the other two are related to the plot, and and also the sklearn is about machine learning, so something more not related to transformer. So I think that we can stop here for. You have a question? Yeah, sorry.
What we did so far was mostly around the word-to-vec method, right?
Yeah.
But now we're doing the BERT, which is more like understanding the text and the context and so on. Like this is the second level, maybe.
Yeah, actually, you get the point. Now we have talked about, I don't know where it was, word-to-vec. That is a technology that was in 2013, so quite before. That was quite interesting also in this case.
Both made by Google, like the BERT we're going to speak about and the one.
Google is very. Yeah. I think I'm not sure about word2vec, so we should check. But yeah, transforming is about Google in 2017. Yeah. Because also the idea of embedding, even if they are static, is something very interesting. Because before they just use features, so something like we have done, like pizza. So just I give you some features about this sentence, and then you use this. But with Word2Vec, we are able to map, yeah, also in the space of a machine, of a computer, these things.
Before that, like we said, like we embed the words into numbers and so on. Like how was it before?
Yeah, before we can see.
Like I think with that, like we had the Google Translate and so on kind of thing.
Before we have the machine learning. That machine learning was based on something related to the features. So, for example, you have a system with different sensors. For example, in this room, we have a sensor of light, of humidity, of temperature. Then you take all these numbers and you put it in a vector, and then you try to process this vector to say that this room is full of people. So in this way, the model can understand if the light is switched on and the temperature is quite higher respect to the normal temperature. You can, the model understand that the room is full, while if the light is switched off, and so this is the approach of machine learning. So based on features and not on representation of the words. So this is the difference. I don't know if you can. I can make some other examples, but yeah. Before, yeah, statistical, just some distribution of probability, and even before, just the rules. So just to put if it is a script and like a test or a tree that you follow.
What brought this? Let's say breakthrough was not the algorithm, but the chips we have, because we have more data and more processing power. So. Right.
Yeah, actually, yeah. Because, yeah.
Otherwise, algorithms or thinking, the thinking wise is kind of similar in terms of programming.
Yeah.
Was it the breakthrough in the programming understanding in terms of algorithms? Which one?
Yeah, the first solution is just algorithm. So you define an algorithm, let's say if this, if that, and so on. While, for example, in machine learning, you have not an algorithm, you have the a model. So yeah, actually, the difference is that in that case you have a network. Yeah, it is. I will explain. It is not a script that you say some instructions, but it is a neural network that try to learn these things. So in the example I made before with the light sensor and so on, you have a training corpus in which you have the input features, so the light, the temperature, and so on, and you have the ground truth, so you have the solution. So given this input, the solution is room full. Given this, the solution is room empty. And so if you give a lot of this input and ground truth, this is the training phase. You have trained your neural network, that is a black box, so made of nodes and a graph. It's something like a graph. And then in this way you have trained this neural network with the weights and so on. And then if I give to the neural network another input that it never seen, it is able to predict the correct label. So before doing training, I give the input and the actual solution, and then I give just the input and and this is called the inference part. So in the inference part, you have just the input and I have the solution. So this is how it works, while in the rule base is just a script in which you write a Python code. Actually, in that period there wasn't Python, but a code in which you say, if you get the luminance of this room higher than 10, the room is full, otherwise it's empty. So this is the approach different. Yeah. And then, yeah, in Transformer we have a more complex neural network that is pretty complex, but that gives you the possibility to learn also about the context of the world in which you have. So this is the situation. Okay, I think that we can stop now. I don't know if I'm in delay or not. Wait. No. Oh, even 4 minutes before, so you have you've gained 4 minutes. So we see in the afternoon for the last time. Thank you for attention. We take the same sentences about Little Prince we saw before, so we can run them to have. Now they are in the list utterances. So okay, the task we try to solve is a task you already seen a bit, that is sentiment analysis. The goal of sentiment analysis is to determine if a sentence is a positive or negative meaning. So if a sentence says something like, no, you cannot make this, it has a negative meaning, while if it is in the opposite, yes, you can, it is positive. So we'll try to perform the sentiment analysis with BERT and on these 7 sentences. So actually also for humans, sometimes it's difficult to understand if it is positive or negative meaning, but overall we can say if the meaning is positive or negative. So the first task that I give to you is to try to say for each of the 7 sentences if you think it is positive or negative. So to make this, there is this table here. You can press, double click on it, and you can put your guess. So for example 0 is hello, I'm happy. That is positive, so I write here positive. If I write also here something else, I can say this is positive, so I write here positive, and then you can close it, and so you can see that the answer is written here. So just a few minutes to say what do you think about these sentences. Okay, we can go on. So now we will see what BERT thinks about these sentences. So we have another set of setups, so we can run it and see if it works. And always in this cell are the configuration parts. So we do not go OK. So it successfully loaded everything, so we can go. So the first part is just we can perform the sentiment analysis on the 7 sentences. You can see here the model we are using is this one, always a distill-based and chased model, but it is fine-tuned on sentiment analysis in English. So it is able to perform sentiment analysis, but only in English. So if you write in another language, it is not able to understand. The output will be something, but it has no meaning. So the task is sentiment analysis, and truncation is equal to true. So if the sentence is too long, it is truncated. Then here we define the pipeline, so we pass the parameters we have defined before. And then we perform sentiment, so the pipeline on the utterances that are the list of, is this list of the sentences. This point, okay, in baseline outputs we have the outputs, so negative and other information. And finally here in this for loop we are printing the solution. And so here if we run it, we have is downloading the model from Hugging Face. As you can see, it's loading the config that says the parameters of the model, self-tensors, is this architecture of the model, the weights are the base elements of the model, and the tokenizer and the vocabulary. And then here we have what BERT thinks about this. So goodbye said the fox, for him it's negative. So because it's saying goodbye, so goodbye is something that you leave someone else, so it's negative. And important score is the confidence, because the confidence measures how much the model is confident about this solution. So he said it is, for him, it is negative at the 98%. So it's quite sure that it's the correct answer. So the second one is only with the earth that one can see rightly, is positive, maybe because it gives, I don't know, a sense of happiness and believing. Then there is what is essential is invisible to the eye, is saying negative, but it is not so confident. So this, and for the other sentences is quite the same. I don't know what do you think about these sentences in from your perspective?
We have labeled them positive.
Okay, all the positive.
What is essential is invisible to the eye. Like we were surprised that it came out negative. Is it because there's invisible in there, or how does the system, how does BERT decide to give a negative?
This is a very difficult question because we don't know actually why. But yeah, how it works is it has this embedding, and it aggregates this embedding in some way through the layers of the models, and finally it gives a final embedding, we can say a final vector, and with a classification layer. So there is a layer that you can imagine it as if the score is below 0.5, it's negative. If it is above, it's negative. So all the transformations, so the things that it learns during the training brings these solutions. Yeah, that's a good point, because also the technician doesn't know why.
Can I ask a question?
Yep.
Here in this, it rates each sentence separately, right?
Yep.
It doesn't interpret all of them at once. So
No, it's sentence by sentence. Yeah, with this pipeline, we are not making a for loop and give each one, because it is managed automatically. So when you pass to the pipeline is a method of transformer, so Hugging Face library always, and so if you give a batch of input, it processes one by one, but yeah, you just give everything to him and he manages it. So because here, if you can see, it is a list. If I remove the commas, it becomes a single text, so it processes it as a single.
Is there a way, probably, for example, we feed the alt text into the system, and then we want the system to take into account the general context of the story, for example.
Yeah, actually,
Then rate each sentence based on that.
actually we can. I can remove the commas, for example, and if I make these, so this becomes they are together. So maybe okay. Yeah, I need to remove here, maybe. So it became, no, doesn't work. So if I make this, for example, and so now these sentences are all together. So if I run this, seems to work. So now if I run this, okay, now I have all the oh, sorry, no, where I am. All the sentences together. So you put a positive mark on all this, on all the sentences together, because this is the input. So if you have a big text, you can just put the text. Yeah, actually, this is, we put together positive and negative sentences, and overall it is a positive. So. Yeah, actually, we cannot be sure that it is meaningful in this context, because of a sentence we can say maybe as humans that it is positive or negative, but if we put more sentences together, also in this case, by reading this, I don't know if it is positive or negative as a human, so, because there are different words that are mainly related to positive patterns and negative ones. Okay.
Yep. Because in English, I guess it's like goodbye is pretty clear, but I was thinking of maybe words like aloha or ciao, where you could be both hello and goodbye, right? So if it was like ciao said the fox, then how would the system?
Yeah. This I don't know, because you should see the embeddings of what you learn. Maybe if ciao is used more times as beginning, learns that is the beginning, so a positive pattern, while on the other side, if ciao is at the end, it's negative. So you can try. Actually, as I said before, this model is for English words, so you should find the sentiment analysis for Italian or other words. So yeah. Okay, now we will try to stress a bit the BERT to see if it is able to distinguish things. Up now, it convinced us a bit, and so now we can analyze, for example, the use of the terms wasted and eaten. For example, by reading the first two sentences, we can see that in the two, the meaning is in the first is negative because you say you wasted your time, while in the second one it's something like positive because it is the time you have wasted for your rows that makes your rows so important. So wasted is positive meaning because we are saying that if you waste time, it's positive because you gain something more. And also the other two sentences are quite similar because the first I wasted 10 years on my career on this project, so I'm bored about it, while the second one says the same but adds, and it was worth every minute. So I enjoy the fact that I stopped at one time. And also the last one is very similar. So if you run it, we can see the solution. So we wasted your time, it says negative correctly. Also The second one, it is able, by reading the context of the sentence, that the situation is changed, and so it becomes positive. You can see that there is also a slight 2% of negative, but the meaning of the sentence is positive. And also for the other ones, it seems to work, because always the added part is changing the meaning of the sentence. Okay, so this to show you this is possible just because we have the transformer, so BERT is able to understand the context of the sentence and change, even if the words are the same or quite the same, it is able to understand the change among the sentences. Okay, and now we can see some corner cases. For example, we have these sentences. So take this is something we already discussed before, because we are combining some sentences together. So, for example, we have what is essentially invisible to the eye, that we can say it is negative, but if we put together something that this other sentence before the global meaning is changing, because we are combining, for example, a positive and a negative sentence. So here, for example, we have that the first is considered negative, but then this part has a higher weight, we can say, and so now it is positive. And also more interesting maybe is the third, where we can see that men have forgotten this truth, so it is negative, but putting this contrastive sentence, but you must not forget it, it completely changes and becomes positive. More interesting is maybe the part 4, because here there are some limitation. For example, the sarcasm and some joke of words that are proper of languages. Maybe, for example, the first sentence, we see great, my train is delayed again. So there is this great, that is a distractor, because for a model can be something positive, great. There is a cool situation. Actually, it is my train is delayed again. So it is sarcastic. The same for lovely. The server crashed right before the deadline, so I cannot work. Fantastic, another 3-hour meeting, so I'm really bored, and I just love being ignored. So they are very sarcastic. And by running this cell, we can see if BERT is joked by these sarcastic sentences. So, for example, the first, great, my train is delayed again, is said negative. So it recognizes that it is a sarcastic sentence, and so it put negative. And also for the second one, it is able to understand, while for the last two, the third and the fourth, this is no more right. Because, for example, in the third, we have fantastic, another 3-hour meeting, so something completely negative, but it is joked by fantastic, and so it's a positive while it is negative. And the same for I just love being ignored. We don't like to be ignored normally, so it is a negative sentence. So, okay, this is this part. Okay, the final part is to try to compare very simply what happened with Word2Vec vs BERT to give you an idea of the change. What Word2Vec makes normally is take the sentence we have. It computes the embedding of each token, and then each token is we take all the tokens and we make the average of the tokens of the embeddings, obtain a single embeddings, and in this case we have the final answer. Looking at this embedding, we have the answer of the sentiment of the sentence. So in this case, we can run this on the same sentences. Maybe we have an error because we don't have Gensim again. It takes a lot of time because it is downloading the model for a Hugging Face, and it is quite big. So, okay. Okay, it worked, and so we have the solution, and okay, no, okay, so I left the whole sentences concatenated, so we have this, but okay, so we can see that in this case, Word2Vec make positive all the words, mainly because since it is not able to understand the relationship among the words in the sentence, just make the average. So it's like for me, it is positive, is positive, there is positive, time is positive, and so on, and then make the mean. So at the end, it make positive even if maybe it is negative, and so on. So this is just a qualitative, I could say, view of what BERT can make. So we have seen that the context of the word in the sentence is very important. As before, I put a very fast quiz at the end. And so if you want to make it very fast, just to understand if the main topics are clear, and we can go further to understand what transformer is, what attention is, and understand why BERT works. Okay, let's see very quickly the answers. So what is the main goal for sentiment analysis? The goal is the number 2, to identify the emotional tone or opinion in the text. Why can sentiment analysis be useful in research or business? Because it can help summarize opinions in many texts. The third one, what is a common limitation of simple sentiment analysis? We can work with the number the third, so it may miss mixed feeling in the same sentence. So if we have contrastive feelings, it doesn't work. Why can sarcasm be difficult for sentiment classifier? Okay, the first one. So sarcasm often uses positive words to express negative feelings. what is the best interpretation of a model confidence score? So the confidence score was the one we saw before. It shows how a certain model is about its prediction. What is a good practice when using sentiment analysis on a large data set? So surely we need to not trust everything, so we need to review at least some examples, so we can see if we agree with the answers of the model. And finally, why does word2vec struggle more than BERT with sentences like I wasted 10 years but I was worth every minute? Because the first one, because word2vec gives a one fixed vector that is then averaged, and so it can use the rest of the sentence to revise another word's meaning. So it cannot put together the information stored in an embedding of a word with the others. Okay, so if there are no questions on these notebooks, we can return to the slides. Okay. Well, sorry for the voice, but I'm losing hour by hour the voice, so I try to make my best. Okay, so now we can move to attention and transformer architecture. So these two terms are very related, attention and transformer, because the transformer is the architectural element or in the model that is able to perform attention. And attention is this capability of the transformer to put in relation words in a sentence, in the input, that are also far away from them. So we can see immediately in an example. Here we have this sentence. Maybe I can use the pointer. So we can see in this sentence, so the animal didn't cross the street because it was too scared. So if we compute the attention to the other tokens of the same sentence, we see that it is strictly related to the tokens that are animal and also didn't and also because. So if we look at the embedding, we will see that the transformation of it is really related to the animal. So this is the idea of the attention. So the core idea is to answer the question, which other words matter to understand me. So I am a token, and I am an embedding of the token in the sentence in which I am, which are the other words related to me. So in this way, we can link directly it to an animal and so on. And this is something that it was very difficult for the models to perform. For humans, it's quite clear, it's simple that it is related to animal, but for the models, we need the transformer to make this direct link. And so this way, we have the attention. To give you a more intuitive example of attention is this example. We have the query, in which we say that I'm looking for information about Italian cooking, and I have these different books in myself, and so I need to search in which one I search as first. So we have Italian pasta recipes, French wine guide, quantum physics, Italian travel guide, Mexican cooking, and you can see that, for example, the book more related to the Italian cooking is the first one, but also book 2, 4, and 5 are are slightly related to the topic because here we have cooking, so the same. Also, French is close to Italy, and Italian travel guide maybe has some suggestion about food, while quantum physics is not related to it. Just to give an idea on bias in the models, it's interesting. I was wondering about this example that I asked ChatGPT to make this example. I give him the query, so Italian cooking, and the example he performed are all about areas that are occidental part of the world. So he selected for example, the Mexican, the French, that are related to the we can say the cultural part of the the Occident. So he never mentioned the Chinese or Turkish cooking, but he selects this one. So this can be also a sign of bias respect to the data. The model has been trained. And so so this is to give you how we can think about the attention in the model. So if we return to our sentences now that were about the first one, and the rose as flower, or and the rose as the sunrise of the sun. So here, with the attention, we can distinguish clearly the meaning of the two words. So, because the first is love this rose, so we can understand that it is not related to the sun, but something else. That can be, as I said before, the flower, but also the feelings of the little prince is experiencing. And while the second one is more clear, because we have just sun, rose, so the model is sure that it is something related to the sun. And also the desert can be a suggestion because it is something related to a place in the world. So and so in this case we can, thanks to the attention, we can see the difference. So at the end we have that same letters, same words, but we have different vectors, because always, as I said at the beginning, we need vectors to represent the input and to distinguish the different words and so on. Finally, here there is a slide that goes a bit more in details, but just to complete the scenario. So actually what it computes a model during the inference or fine-tuning and so on are these three elements that each element tried to take a different information inside the input. So the query is just what I'm looking for. So it is related to the question that you are performing, and the link of the direct link with the token with the word around it, and the key is something more related to the I would say is my label. So it is what we called before the embedding similar to word to vec, and finally the value is the semantic content. So in one case we try to understand the general meaning of the word in the sentence, while the last one is the embedding. And then we can perform some computation and finally obtain the score. And yet the important thing is that our word to vec embedding, there are the values are multiplied by weights, and these weights changes each time the sentence changes. So this is just important. This is the passage from just embedding and embedding with transformer. I don't know if there are some questions about this topic. This is just a brief introduction on what attention is, and yeah, I put some formulas but are very basic. Okay. So now I'll introduce the idea of the transformer, and actually I'll start with the last one. Okay. Here we have in 2017 we have a very famous paper that says attention is all you need, and they gives a model that appears something like that. So we have an input, a textual input. Then we have an encoder that is something that tries to take the input and extract the meaning that is inside the input and creates a representation. That is the embedding multiplied by the weights I was talking before. And then thanks to this internal representation, thanks to the decoder, it is able to spread this knowledge in the internal representation and create the output. So the idea is to, for example, to train this model, this architecture. One solution is to give an input, hello, I'm Giovanni, and create internal representation, and the output is reconstruct the input. So a way to train the model is this. I give hello, I'm Giovanni, and the output must be hello, I'm Giovanni. So in this way, in an iterative way, we can train the encoder and the decoder, these two huge models, to make this, and internal representation must preserve the semantic and the knowledge that is present in the input. So in this way, the most famous encoder-decoder architecture is the T5 from Google, and the main goal of an encoder-decoder structure is to, for example, to summarize or translate. So a common task is take, for example, a 100-page book and try to make a summary in just one sentence. And over here we have all the tasks, summarization, translation. For example, for translation it's very important because we have that in input we have a language and we want another language in output. So we want to see if the internal representation is able to memorize the actual meaning of the input in a language, and then transform through the decoder the same concept, the same sentence in the output. And so every task that is specific for the decoder structure is always something that I need something to understand the concept and then transform this concept in something else. So for example, change text style. I write an email and I want that this email is for my supervisor, and so I need to change the style in a different manner. So the internal representation must be the same among the informal one and the formal email, but everything is preserved. So this is to present you the encoder-decoder. So this structure is the complete one that is the first release, and in this paper that they suggest the attention this new very important topic. So in this case, so after this, we can see that actually we can also use the two elements, one alone. So the first one is the BERT. So BERT is the model we already seen, and it is an encoder-only model. So now we can understand why there is the E in BERT. And the idea is to have an input, and the goal of the task must be to create a representation of the input. So, for example, in the sentiment analysis, before we have an input, a sentence, and then we want to understand. We want to, as output, a aggregation of the information contained in the input to have as input a sentiment of the input. Another important task that BERT suggested is the masked training. So the model must fill the words inside the sentences, and it is very important because to fill the correct word inside the sentence, you need to understand the whole context. So, for example, in this sentence, it is only with the that one can see rightly. If we see just this sentence as it is, we can fill it with eyes and not with earth. That is the actual word in the Little Prince book. And so, yeah, you are reported some tasks about the BERT, so text classification, document semantic retrieve, and question answering, and document clustering. Document clustering is something like we seen before with king, man, woman, daughter, and so on, because if we have a single representation of a document, so a bullet in the vector space, we can also make some clusters about the documents we given. And so it's important to say that the encoder, the goal of the encoder is to understand, you say to find our representation. So it is not a generative architecture, but it is just try to understand the meaning of the input. Okay, so this is BERT, and finally we have the decoder-only architecture. That is the architecture that, for example, GPT uses. So it is all the LLMs, all the models you use online are decoder-based. So we have given an input. The model try to predict the next token as output. So it is, I put that arrow as loop, because every time we have an input, the sentence, then we predict the next token, and we put again is input the whole sentence plus the new token predicted. And so we can ask the decoder to predict token by token. And so in the example, it's only with that it can guess help and then guess off and so on. So you can continue iterating the generation. Finally, these are the main tasks. You can use the decoder, so for generation mainly, so text generation, brainstorming, and so on. And this is okay, so it generates fluently, but it is not able to obtain a representation. See, yeah.
How what OpenAI did is different from what Google was doing, you know, in search engine. Like when we write something, he says, "Did you mean this?" or tries to suggest things to us, you know. So what happened exactly? Like what is the difference now?
Okay, yeah. Okay. Actually, this OpenAI is to give you an idea of the scenario. The first release is this by Google, and in the beginning of the 2020, they think all that this was the solution and so on. But after this, actually all the competitors, also Google, arrives to this other solution, saying that the decoder only is a better architecture because it is faster respect to the encoder-decoder. So this allow you to actually to generate text, so to continue a sentence. You don't need to understand deeply all the input you have, but you can use a unidirectional input. That is the one you are using in the decoder. So this is the how it works is mainly during the training, the decoder learns in the layers all the how to represent the language, for example, English. So it is able to to store this information inside in the weights of the network, and then the passing, the input passing inside the layers of the decoder. At the end, we have a probability of which is the next token most likely is next, and so we can add to the input the token comes later. So in this case, you have that it is only with the, and you can put as next token the word help, and so and again make the same process up to the end. So OpenAI is the first that for that the encoder-decoder is not really useful to have a speed generation of text, but it is the decoder only is enough. Then after OpenAI, also the other models selects this approach to generate the text that when you go to a chat LLM, you find a decoder that processes your input. So I don't know if I get to the question, because I think that was quite different, but I didn't get I don't know if it's okay or not. Maybe we can talk later. Okay, so this is, so I stressed you about the architecture we have, just to try to give you an idea of how it works and when to use each one, and it's important. So we will have a notebook, but I think that we can make a break now because, okay, well, we are quite at the end. If you have understood everything now, you are quite an expert in NLP. So now we try to put in action these three models try to understand the purposes, their purposes. So we'll see BERT as encoder, we will make again sentiment analysis, but also the mask language prediction. Then there is GPT, so the decoder only. We need to, we will use it to complete text and see that is every time different. And finally T5 encoder decoder to have translation and summarization. So we can go in the new notebook, the number 3. Okay. So this notebook, at the beginning you have a very fast summary. This table is saying, the architecture style of each model, the task of each model, and we can say how the model works. So it is the main risk of the model. So here we have always our setup that we need to run at the beginning. And we have always our passage that we already know very well. Okay, and so we have this the print of the passage. So the first task we solved is BERT. So here we have just a reproduction. For completeness, I put again the sentiment classification here. The code is the same as before. We are using the same model, and the parameters of the pipeline are the same. And so now we have the target line. It is this sentence. So this sentence is positive, and I think we already discussed a lot about this. So there are no questions about this, we can go directly to the masked word prediction. So the masked word prediction, as I said before, we will have a sentence with a lacking token. The text is this one, the sentence is this one, and we have removed the original word art. Just to know, these passage mask items, this is always a list, but it is, I don't know if you know, a list of dictionaries. So we have the text that it is this one, and the key original that is art. So in this way we can see which is the text and the lacking token. So we have these examples. So another example is what is essential is to the high, and the last one you become lacking token and forever for what you have attained. And finally an example that is not related to Little Prince, but it's about the weather. So we have the masked token that is hot. So here we have a function that just is used to print the results. So it takes the list of dictionaries, or this list here, and print the solution. So just to know, if we write this item of text in this way, we are taking the key text of the dictionary item. So here we can execute we have the pipeline we have defined before, fill mask, this pipeline with always BERT, base model, fill mask, and also we want top k equal to 5, so we have 5 possible words that can fill that mask token. So if we execute this process to the 4 sentences, we have this output. So let's explore them. So for the model, we can see that the most interesting, the most related words to fill this mask are this one, and we can see that Earth is not here. So this means that the most related words are high, and just because the model in this sentence has no idea of this sentence, that this sentence is of a book that we know, so the Little Prince. So also in this case, also again, this sentence is in contrast what we put, because what is essential normally is visible to the eyes, and so for him is visible. But actually we see that in the third position we have also invisible. And finally the last one, the third one, you become, and the actual solution is responsible, and again it is in third position. And finally here actually the weather will be the most common word put it after will be is hot, so the rank is okay. An interesting thing to notice here is if we try to give the model the idea that this sentence is about the Little Prince. So if I put before, for example, this sentence that this is about Little Prince as the input, for example, like something like that, we can see if the score changes. Before the position of the correct, and of the correct word responsible was the third one, while now I put the Little Princess before, so now the model can understand that the sentence is about Little Prince, so the score now is that responsible is as the first solution. You can try also on the others. I already tried at home, and I think this one should work, while the first one no. No, actually in this one, it's it doesn't even it is worse. So yeah, it is not. It don't works, and we can try also in the first one. And also in this case it should not change a lot. So yeah, the high is always the same, but if for example, I put 10 here, so I take 10 words. Earth is present, for example, while if I remove Little Prince here, Earth is no more even present. So to BERT, if we give a context in our input, it is always important, and it improves the performance because it is able to understand the context of the sentence. So also for a human side, if you know the context of the sentence, you are able to give a more specific mask. So, okay, this is for. We have finished BERT. These are the two main tasks in which BERT is used. We can pass to the task B, that is T5 based. So T5 is the model encoder decoder that we use for text to text. So always we have an input, we want to create a representation of the input, and from this representation we try to define an output, to generate an output that is related to the input. So the first task we can see is the summarization. The summarization, so we have a text and we want to summarize the content of this text. So here we notice that we are changing the model. So we have T5 small. T5, there are a lot of dimensions, different dimensions. So we are taking the small one to speed up the process. And then in this case are also important these keywords, because we are saying which is the max length of our output. So we want an output that is maximum 50 tokens, while here we have a min length that we can define. So we need at least 20 tokens as input. And okay, do sample for okay. And so here we define the model without the tokenizer and so on. We define our pipeline that is summarized, so in which we give the task, the model, and the tokenizer it needs. And here we can run it. We always download the model, and there is an error. Wow.
The summarization didn't play on
Yeah, I'm noticing. I don't know why it's an error. Pipeline. Okay, summarize pipeline. And no task summarization of all tasks are end-to-end, auto classification, automatic speech, depth estimation, document cost. Okay. We are selecting the wrong model. So because T5 small as it is, it is not able to make the summarization. So we should search. We can try with this. Okay, we are taking a model not so used, but we can try. Or we can ask ChatGPT to solve the problem, so, or Gemini, and so on.
is it could be from translation and suggesting using another model.
Yeah, I need. Yeah, I'm trying to use another model.
Helsinki.
Hmm?
There's a model that Gemini is suggesting. It's Helsinki/NLP.
Helsinki. Let me search for it. Helsinki. Oh, what is the name? Or
/NLP then
Opus.
French English.
Yeah, this is for translation, not for summarization. I don't know why, but yeah. Okay, closer to should be.
What of text-to-text generation?
What?
Text-to-text.
Yeah, it's the structure of the idea of the autoencoder is to have text to text.
I think that's what Gemini suggested here.
It tries to just to put. Text to text.
Again, text to
It's a suggestion come from Gemini, but it's not working for Sosyal. Yeah, there is another error.
Let's make it working.
I found something working, but I don't know how to send it. I just followed what Gemini said. I don't know what I'm doing.
Okay. Oh. So which is the model I suggested? On
Auto model for seconds to seconds. I don't know.
okay, but it is.
Maybe I can copy it.
Ana şeye girerseniz oradan hoca görür. Kopya olan değil de.
Hocanın konusu.
Tamam, öyle.
Give me a Okay, maybe I can. Can I take? Okay, just load from pre-train. But it doesn't define the
It seems it works, but I don't know.
summary tokenized generate. Okay, yeah, it's not using the pipeline solution. Yeah, this just okay. Auto model for safe. Okay,
Do you want me to copy it or you don't?
can be. If it doesn't work, we'll. Okay, I think that actually it is not so important, this part. So just to give you, I don't know if you want, yeah, you use organizer and generate directly, not pipeline. Okay, let's see.
Maybe because you're using the low model, like using Gemini Flash 2.5.
Yeah. Yeah, we can. That's still failing. Okay, now it's working. Okay, the changes. We have changed a bit. So before we tried to, because I didn't put the token of a game face, but this is not useful. We can delete it. Then we have we are maintaining the same model, and actually we were loading the wrong model. So because we're using auto tokenizer, so for the tokenizer is okay. Here we have this, and then we are using not the pipeline, because pipeline is a high-level method to that it performs directly all the operation, but the keyword summarize is not present in this pipeline method. So we need to enter inside the pipeline method, and so in this case, differently from before, we are making encode. So here we are making the operation of the encoder, we can say. So we are creating the input IDs. So here we have the prompt to summarize. Then we have some input, and here if we print input IDs, we see the token translated into the embeddings. You can see we can put, for example, a print here. So here you can see all the embedding. So this is one embedding of the input. So this is the final representation of the encoder. And okay, then we have the method generate to have the process continuing. So we pass the input IDs, and no, actually I made wrong, sorry, because the encode just translates the IDs of the tokens related to the vocabulary. So these are the numbers of the vocabulary, of the IDs inside the vocabulary. So words that are, for example, free, these are two tokens of the same, two equal tokens. Actually, this generate is the things I was talking before. So is the summary output. So this is the output of the encoder and decoder. So we have just summary output. So if we print so this is the representation, is the tensor of the representation of the output. And then we can, to pass from this, we need to pass from the vocabulary. And again, map these tokens, IDs of the vocabulary to the final solution, that is the summary text. So here we have that for each word that we can see in the summary. So 0 is man, have is 1076, and so on. So here we can see the vocabulary. We don't see the embeddings, but with the ideas of the vocabulary. So now we have, at the end, we have our summary. So starting from the prompt, that is summarize these things. We have the output, that is a summary. So we can change some parameters, for example, the max length to have a longer summary or even shorter. A small note about this is that here the model decides what to put in the summary. So it has only the constraint to output maximum 50 tokens. So if we give too long text in input and we ask for a summary very short, we lose information and so on. Okay, I'll upload the correction of this code on the notebook on the link. Yeah. But in this way, we have seen, yes, we have seen the.
Could the problem in the code be what was written in the bracket itself? So we have like t5_model_ref. According to the correction I had, we're not supposed to have ref. It's supposed to be ID because it was written the first time. I mean, is that a problem?
Sorry, I didn't. The ID.
I'll show it to you instead of stopping the entire.
Okay, maybe you can. Okay. So actually, in this way, we even if there was an error, we have seen in more details how the pipeline method works, and so the different steps it performs. So an encode, generate, and decode. So remember the pipeline I showed before about text to numbers and so on. Here we can see it in details. So let's see for translation. Maybe also in this case it doesn't work. It's strange because I run it, but it doesn't work. Okay, we like this, and it's not a problem because no. Translator is not working. Sorry for this. Maybe we can ask Gemini, that is always useful to fix also this.
Will you run a local model in your Visual Studio Code?
Yeah, actually, yeah. Now we are running the a model on actually Colab is a service that is outside my computer, so it's running on a server that is online. So now for this simple processes, we can use just CPUs, so RAM and disk. But in this case, we can also ask for more resources, so also for GPUs. And so if we change runtime type, we could ask for also GPUs. So if you use bigger models, you can ask for GPUs. But this is a queue, so if a lot of people ask for this, maybe the resources are not available. Okay, so now we have translation.
My translation doesn't work either because of the summarization.
Actually it is very annoying, these things. Sorry for that. I can put directly the new. You can ask to Gemini to fix. So.
I apologize for interrupting. I got a new error message saying the cell's output block is empty in the current state.
Also, this is another error. Arrive. Okay, sorry, it is empty. You need to run, I think, the first corpus.
I thought I did, but
this is executed, okay.
Yeah.
And the error is okay. And if you run this, okay, I put the solution in the notebook I shared, so it should work. If you copy and paste the other.
okay.
Okay, so now translation, okay, is working. So let's see. So T5. Now I'm trying to translate from English to French, and so I have this English line with the same sentence, and I can see that now, always it change in code, generate and decode, and again we can see that the translation succeeded. So we have the English source, then we have the French solution. I don't know French very well, but it should work. You can try with Google Translate if it is the same meaning. And a very important thing is that actually T5 has been trained just to translate from English to other languages, and also the other languages are very, very small amount. So for example, if I try to take this sentence in French and put here for simplicity, I call it English line just to we can change in this in French line. Then the source line is French line, and if we see what happens, we can see that the model takes the input, but it is not able to translate this sentence, and so the output is just the source text again. So here we have a limitation, for example, of T5, that is just to translate from English to French, maybe German, and also Romania, and Roman, also, that's also. And so this is a limitation. But we can have other models that are fine-tuned, always based on T5, in this case Opus, and are fine-tuned on the specific translation. So for example, this is from French to English. So we can try to run this. That doesn't work, or maybe, I don't know. Okay, now it's working. Perfect. No. Always pipeline, I don't know why today pipeline is not working more. Maybe because the pipe, but before we use. Okay, we need always to fix these things, and so always ask you to Gemini fix also this cell. So the idea is always to split the pipeline into encode, generate, and decode. So now okay, fix this. Then we need to fix also this. Okay, we have loaded all the weights of this.
There is an interesting thing. When I changed the French, instead of writing French, I wrote Turkish.
Okay.
Then it translated to Dutch, not Turkish.
Ah, okay.
So maybe define Turkish as a Dutch language.
Yeah. Actually, the idea is that you have encountered the hallucination. I don't know if you heard about the model. Hallucination, that is a behavior of the model which doesn't know what to do, and so it outputs something that.
It doesn't know Turkish, or there is no definition for Turkish for this NLP. So it's take that.
Yeah.
In the end, so it said Dutch instead of Turkish.
Yeah. It's a good observation. So now we have this new model that has been fine-tuned on French to English, and so here if we give the sentences in French, we can have the output in English. It's interesting to notice that the sentence was changed by the model. So the original one, the reference was this one, the last one, while the model output is this. The meaning should be the same. You can only see with the heart, and the sensor is invisible to the eyes. So, but the perfect words are different. This because the representation inside the model is not able to catch all the words perfectly, but just the meaning. Okay, so after these operations of translation, actually of this Helsinki NLP model, there are a lot of possibilities. So there is a guide, so you can change just these. For example, if I put year and year, you can switch it. Or if you want to use Italian language, I think that is IT, but for Turkish, for all the language, there is 2 letters that you can put and select the correct language. Yeah. So, and it's interesting to notice that all these ones are different fine-tuned models. So we start always from the base model, the base model, but then for each one we have fine-tuned it on specific language. So this one is able to translate from English to Italian, but if we switch, we have another model that is always the same base model. So the architecture of the model is always the same, but the fine-tuning process is different. The data on which the model has been fine-tuned is different, and so the weights of the model are different. And so these 2 models, even if they have the same architecture, they are able to perform different things. Okay, so this is the last task for the T5 translation. Then we can go further to the GPT architecture. And so GPT is an encoder-only model, as we said before, and it is able just to predict the next token given an input. And so now we can try to run this if pipeline is okay. I'm scared about this. You can see. Okay, here, always the structure of the code is always the same now. Also pipeline worked. And so the sentences we are considering to continue are the ones in the before. So we can see here the parameters we give, and here we have the sentence that we performed before. That is, it is only with her that. And I asked to the model to, I don't know where it is. Okay, yeah, to return two possible continuations. So I run GPT 2 times. So here is because we have 2 continuation. So we see that we have given an input 2 times the same exactly word, but we have 2 different outputs. This is because the models are not deterministics, but are probabilistics. So for example, here we can see that a continue, what is sensitive to is invisible to the eye, and then you continue saying it is only with the heart that one can see rightly, and this is what we can say of the most fundamental of all objects, the mind. The heart is the only sensible being, the world, and not only the one of all things. It is the very essence of the world creation. So you can notice that far we go in the generation, and less the if you read the sentence and if you go further, the meaning of the initial sentence is lost. So here he's talking about the mind is the only form of all things. So and it continues. So in the first place, mind is our consciousness. So we are changing topic completely from the first question, the first sentence, and so this is because we are forcing the model to output 50 tokens, and so it tries to fill in some way the output, and it don't know what to say, so it continue generating, and each time the most. So if we are at this point, the next token is always the most likely, the one that is more, that has some higher likelihood in respect to the one before and the sentence before. So again, in continuation number 2, we are giving the same sentence, but now it's with outputs on our contrastive sentence. So on the other end, one can discern from sight, but one saw something may be related to, but no meaning, and so yeah. Here it is repeating the same sentence and so on. So it's very interesting to see these things about the generation. And then you can try to change the sentence. So, for example, making a question is interesting. So if I find the input, so it's generator target line. If I write hello, how are you? You try to continue this input with the answer. It is quite slow, the generation, because GPT starts to be quite big as model. So since we are not using the GPU, so the fast execution for the models, it is running on a CPU and RAM, so it is quite slow. But now it is continuing the question like, hello, how are you? And then it said, is there any medicine in your stomach? And it's okay, here, I guess some, it's everything right. So I don't know why it is outputting this, but it's okay, yeah. Here, for example, has more meaning because say, okay, how are you? So it thinks it is a speech among people, and so there is this Kana that asked to this question to the interviewer. So this is the part. So here we have the final comparison about the different. We have all the tasks. So BERT for sentiment, must guess, while T5 summary and translation, and finally GPT for continuation. And yeah, the idea is that depending on the architecture we have, the model will be better for a specific task. For example, also other, for example, also the models we are using, Gemini, for example, if you ask to translate something, it is able to perform the translation, even if it is an encoder-only model. But this is because they are becoming very powerful models, and so they are able also to store the meaning inside of different languages. So it is able to generate the most likely tokens are the ones of another language. So if you are surprised because you can ask to Gemini to translate something, is not because, even if it is an encoder, the answer is just because he learned in his data set also words of different languages. Or another possibility is that there are some layer of translation before the input to the model. So Gemini recognized that the input is not English, so he before use a small model to translate, and then it inputs to the big model. So these are the last takeaways. I already stressed you about these things, and now is quiz time. So there are some quiz about the three main architecture. So I give you some time to face them, and then we will check together. If there are no questions, and so. And maybe some cultural elements and so on. Then GPT-2 is used to continue the line with generate text. So we already seen that we just predict the next tokens one by one. And what is the central question of GPT-2 in the notebook? And here is the number 2, because as we have seen before, it can sound fluent and can joke us, but this during the generation it can drift from the original argument. And finally, the larger elements, the lesson emphasized by comparing BERT 5 and GPT, the number 3, so different architectures perform different tasks and have different failure models. So I stress a lot about these things because these are different architectural choices that can help you in choosing the best model for your specific task. So also this notebook is ending. If there are questions, are there questions? No? If there are, okay. So.
GPT-2.
Yeah.
There's a parameter that we adjust how long is gonna do research?
Yeah, here we can see here this number. So we can say yeah, the maximum length of the answer. So if you increase it or reduce it, the answer will be shorter or lower. And yeah, here there are also the temperature, other parameter like temperature and top K. That's very important is the temperature. That is a score that explain how much the model will try to be, how to say, creative, yeah, correct. And so here is quite high, and so it has been a lot of, it has been creative. If we put a smaller number, maybe it is more rated to the topic and try to output it. I don't know, but you can try to change. It is running, so change the parameters and see what happens depending on them. So also, also top K is parameter because when the decoder is predicting the next token, actually it doesn't output just one embedding, so one token, so one word, but it outputs I would say a score, a leaderboard of the probability of each token, and so this we say you randomly pick among the top K. So you take the top 50 tokens predicted and select one. So this is why. Actually, it is not randomly taken, but there are the weights that are the probabilities. So if a token is very likely, it is the one that is selected. But in this way, you can select this randomicity of the model. So yeah, actually now we have put the temperature equal to 0.1. So the model is less creative, and so now here we have hello, how are you, and we have an answer, and we can see that also the structure of the output is very similar in the two continuation we have. So in the same, they see I'm a little bit of a nerd, and so here the beginning is the same. So. And then here is repeating always the same because since the temperature is very low, it's just filling the maximum number of tokens with always the same sentence. So this is why. And yeah, these are the things about GPT.
Is top K and temperature are related, like with the
yeah, actually, yeah, you can use it because if you put one, you just take the most probable token, so you take always the same. So yeah, you can normally the parameter that is considered is the temperature. So normally you work on this. Normally you don't manage the top key because it's something too in details, while temperature is something that you can work depending on the task if you want the model more creative or not. So yeah. Okay, thank you. So now we can make a small break, and then there is just a last notebook in which you can try working on this topic. I present some small tasks and you can choose which task to solve, and using Gemini or copying and paste the parts we have discussed, you can solve them easily. So we can encounter us in a while. Okay, we are quite at the end. So this I present to you this last notebook that you find as notebook number 4. That is an open book notebook, so there is no code inside except for some setups. The idea is to that you can try to code inside by copy and pasting the code we have seen during the lesson, or you just ask to Gemini. The idea is there are 3 scenarios that we don't know with which model we need to solve each one. And so the first one, we have some text about an interview. So what do you think about cities, public transportation? And we need to perform some operation on that to understand if it's okay. Then the scenario number B is we have a long text and we need to understand quickly what it is about. And finally, the last one, we need to write a politician speech about a topic that is given. So if you don't know what to do this evening, you can perform these exercises and just try to understand which models you need. And it is quite simple, but if you put some effort in this, you can understand better something else. So the last slide I present is just the beginning one. So we can return to the questions I started the lesson and are the same one. And here we can understand why these things are not possible for a model to be solved. This is because they are not strictly related to text. So the model nowadays can learn just from text and what you can learn from the input data. So everything is, for example, in the child, it needs to study the photos or the description of the dog, while a child can experience it. So it uses all the sense, like the eyes, but also the other ones. So here is just the answers at each one. So the bar exam is simple because it's text, so you can learn everything, while driving is a physical experience, so you cannot manage it. The same for the pain is a sensation, it's not a pattern of words. And also to balance in a bicycle, it's a memory of muscle. So with text is difficult to describe. You can describe it, but you cannot experience it. And so the same for the child, because the child is multimodal, so can learn from different sense, and by touching the dog, by listening the sound, and so on. And so this is everything for today. So thank you for the attention, and I hope you enjoyed this lesson. I try my best effort, and okay, thank you.